Hello, in this video I want to discuss with you possibilities to assess the quality of a groundwater model. Well, first of all, what do we understand as a quality of a model? So what is a good model? And in the past lectures I introduced you to a couple of characteristics of a model that are associated usually with something we call a good model. So a good model, of course, is stable, right? So it fulfills the basic demand that we can have on a numerical model, that it's stable so that its results are at least have the chance to be somehow reliable. Right? A good model we also often associate with the terms of accuracy. So that the accuracy of the new model is within a range of uncertainty that we can accept. All right. Much harder. Well, we can let's talk a bit more about accuracy. So to actually assess the accuracy of a model is difficult. We talked about that in the past. It's all right, you can compare it to field data, to laboratory data, to validations or verifications of the model, but actually assess, like qualitatively express the different errors a model can have is a challenging task. But we can maybe through parameter variations or so on get an idea about how accurate our model is. Much harder to check because it's more on a conceptual model and just as an observer with someone who's not developing the model it's yourself, but if you just have to judge about the model someone else did, it's much harder to judge the conceptual decisions made, right? So how applicable is the model to your specific situation? So are the physics captured correctly? Are the boundary conditions representing the scenario as it is in reality? There's a question which might be much harder to find out, which require questions or require documentation of the model. And there's also something what you could consider as a qualitatively model is a model that is well documented, that is reproducible, right? So there are a lot of different aspects. So this list is by far not, has any reasons to be complete. It's just bringing up terms we've talked about in the last weeks. So you have conceptual decisions which might influence what you consider a good or bad model. And related to this one is every model is by definition, and I keep repeating myself, I know, but every model is an approximation. Approximation means there are limitations of my model. These can be computational limitations in terms of memory space, computational costs. So what I have available in spatial or temporal resolution, in the complexity of the physics that I can represent. These can be limitations in terms of how much data do I have available to actually parameterize my model accurately. All this will also influence maybe what you consider the quality of a model. But it's also, from an external point of view, quite difficult to judge. So this is why this developer perspective, so the perspective of the person who actually conducted the simulation, is so much important, because this person has the best feeling for those kind of limitations, also for sensitivity with respect to, for example, parameters or so on. Right, so I just want to point out here that what we consider a good or bad model is really much depends on your perspective, on your demands, and also depends on the level of understanding that has to be achieved with the model. All right, so this is really no complete list, and that's right very much emphasizing that there are a lot of other things to judge. I will focus on one, in principle, very simple model. If you follow the other videos, you've came across this example maybe in the past a couple times. It's a trace injection into a heterogeneous aquifer. So we have heterogeneity in hydraulic conductivity and porosity and diffusivity. You see exemplarily here the hydraulic conductivity field. This is just to, to have a bit more complex flow field, to have, a bit more interesting things going on. We have a very simple still boundary condition, so simply stream from left to right with a hydraulic head. And in this steady state flow model, we're introducing a tracer concentration, and it's a point source. So I initially injected had an initial concentration here of 5 kilograms per cubic meter, just simply in one cell. This now image here is taken after a little time, so a little bit has already diffused. So that's why the maximum here is 4.7, but that's just because of the diffusion process. So what we expect is that this initial tracer diffuses, gets attracted through the heterogeneous flow field, and as diffusivity is aligned similar to the hydraulic conductivity, it means regions of high hydraulic conductivity are also associated with a high diffusivity and a high porosity. This trace concentration is supposed to follow somehow these high conductive regions. So in principle, a very, very simple model, but using this very simple model, I will apply modifications to see how this will affect the outcome of the simulation. So first of all, this is simulation results, as I show you. So after 5 days, we see what is expected. The tracer concentration diffuses and it vectors in flow direction. At the beginning, quite simply in one direction. We see then that with advancing time, the heterogeneity takes place. So this one is not as symmetric as expected before. It gets a little bit curvy. We see this trend continues as we follow this heterogeneous hydraulic conductivity and diffusivity field. So this is to be expected. We further see that the tracer concentration, so the maximum tracer concentration, of course, is decreasing over the 30 days of simulation. That is also to be expected. So this is all those indications very much is what we would expect how the tracer to behave. So we might have, from a first perspective, quite some trust in this simulation. And we will now study this simulation and variations of this simulation in more detail. So within Trust.js, which is a software I'm using to conduct this simulation, there is a statistics tool which, because it's based on a raster map, analyzes you the value within each raster map. And if you generate this output, we nicely see interesting values here. I will pick out the two. So this is now for the 30 days. And you see we have a minimum of 0 for the tracer concentration, which is perfect because this is the maximum. The minimum we would expect. We do not expect negative tracer concentration. That would be an unphysical solution. Well, we have a maximum. We have already seen on the other maps that this is decreasing over time, so this is nothing new information. But we also get a sum. So here it simply adds the tracer concentration in all cells, and this should be similar to what we initially injected. So we still want to have our 5 kilograms per cubic meter. And we see we are within, well, some reasonable numerical accuracy, quite close to it with 4.9976 and some more digits. So we can make, just from this conclusion, or from this simple analysis, 2 conclusions, which strengthen our trust in this simulation, because we know, okay, the solution is bounded. So we're following we have values between the minimum and maximum physical values which we would expect. This is good, and we see the mass model is the model is mass conserving because if we get all available tracer, we still come up to our 5 kilograms per cubic meter because we didn't use any kind of decay or other kind of mass vanishing methods. So this both strengthens our trust into the model, and especially the mass conservation. I remember that CrustJS groundwater flow module, as well as the Solute transport model, is based on finite volumes, which is specifically well suited for the mass conserving. So here we see one of the benefits of that kind of numerical implementation. As a next step for analysis, we can also look at the output in the command window, which provides us also with interesting and important information. Right, again here I'm using CrustJS, but pretty much any kind of software you will use for groundwater modeling will provide you with some kind of command line output, and I always recommend to take a look at this. In this specific example here for CrustJS, we get interesting information about the current Friedrich-Levy stability criteria in the Solute transport model. So here, for example, it calculates the CFL value, which is 2.9. And as you hopefully know, and if you do not know, I recommend to watch one of my other videos. This value should be smaller than 1. So the program itself calculates the highest possible time step to fulfill this criteria. And it says, well, the time step I'm inserting here is way larger than this criteria value. However, as you will see here, I use the command option to split this time step into 10 fractions. So it will actually compute. So this is not my actual time step that it's computing, but it will compute 10 time steps until it has reached this total number. And then for this total number, I will generate an output. So this is a very neat function. We will talk a bit more about the other ones here as well, but you can see all the different time steps here. Well, the kind of solver that is used, we do not matter. But you see, for example, well, we only have iteration 0, so he doesn't need much of iterations to come up with a error value, which is quite small. So we're already at 6 point something to the power of 10 to the power of minus 10, which is really, really small. So it doesn't iterate very much, and it's compute quite quickly. Right. But here the focus is on the CFL criteria, which is fulfilled because I'm using these kind of splitting things to have 10 loops actually within the one time step that is calculated. So in principle, if we have the CFL criteria as like the most popular, most reasonable criteria for stability in numerical simulations, you can apply that for different kinds of equations and different parts of equations. And the way it is implemented in CrustJS, it's based on the advection. So you have velocity multiplied with the time step divided by the spatial resolution, which in my example here was 2 meters. And this is the CFL value, which should be smaller than 1. Well, you can do the same one for diffusion. Of course, the implementation always kinds of, or the exact definition of the CFL value depends on the numerical scheme you use. So here I did this because it was accordingly to the lecture about the stability criteria. Look in the other videos for centered in space, forward in time method. So then you get these 2 here. But note that we here have similar units, right? So in the end, it all has to be, all units have to be equaled out. And we have here the dx squared in comparison to the dx here, but therefore we are not having velocity here, but the diffusivity. But note that if you divide diffusivity, which is a meter square per second, by meters, you end up again with a velocity which is meters per second. So both equations here are equal, right? Or both represent the CFL stability criteria, just one for advection and the other one for diffusion. Why does GraphJS solid transport model only checks for the advection? Because under most terms, advection will be the dominating part for in groundwater transport processes compared to the diffusivity, right? So that's why it will check the advective part. So another important point to note here is the module, solid transport module implemented in GraphJS is using an implicit method. So it is unconditionally stable by definition. However, remember again, stability and accuracy are two different pairs of shoes. So you need to reduce the time step to come up with a good accuracy, and the CFL value is a good approximation for this. So in terms of time step or size of the time step, you're not gaining much using implicit methods here, but this is also something I've discussed in one of the other videos. A bit more background here on the Friedrich-Levy criteria within GraphJS. Again, if you look into the source code, which you can do because GraphJS and all its modules are open source, you will find that the CFL criteria is only implemented for the advection. Fine, we discussed that on the slide before. If you use a graphical user interface, you can set a flag for the CFL criteria, so the module will automatically use the time step that fulfills the CFL criteria. Due to a bit of a not very nice implementation, you can't use this flag in a script based on Python or other, but there are different there's a different approach or workaround. You can use so-called loops. That is what you have seen in the slide before in the example, or in 2 slides before. What I did there, by simply dividing the time step you give as a total into sub time steps. In my example, I showed you a couple of slides before, it was 10 loops, so that each of these sub time steps computes or fulfills the CFL criteria. Right, but this is just a workaround here to make a bit clear how the CFL criteria is implemented within GraphJS. So what happens when we violate the CFL criteria? All right, and you see here I did not use these kind of loops, so it's taking the time step as it is, and you see still it just needs 0 iterations, so just one iteration actually. You see, okay, it still has a pretty small error. The error is slightly higher than has been before, but it's still sufficient that there is no further iteration required, which first of all is fine. It doesn't say as much about the stability, but if you look again on the similar information we had before, we first of all see, well, that looks different after 30 days than the previous simulation. We see something like, oh, there are negative values. And this is also, if you look in the statistics, we see here, yes, there are negative tracer concentrations, which is unphysically. So our problem is not bounded anymore. The total sum is still pretty good. So it's still mass conserving, but of course, having negative values also influencing the total sum. So might be that if you continue the simulation for further days, this might change or not. But this is a warning signal, and it might be difficult for you to see for you in the videos. But if you analyze the 2D trace concentration, you will see, well, okay, there are unphysical symbols, or structures, better to say. There are structures, kind of a waveform here, which of course there is no reason for that. And if you actually dig deeper into, you will find that the negative values occur here. Up here, you will also see similar structures. So these are structures we do not expect in such a simulation, right? It's a waveform, if you're not actually modeling waves, are always a warning signal with regard to stability. So here we have several indications to say this simulation is unstable, right? And again, the problem is, what means unstable here? It's an implicit formulation, so it is stable by definition, but it's inaccurate, right? We're violating boundedness. We have here unphysical structures. So this is all warning signs now in terms of a low quality of the simulation. So we can do the opposite. We can reduce our time steps. So I previously used 10 loops. So I had my time step of 1 day and I split it into 1/10 of a day. This is both a random choice by myself. So I can check what happens if I decrease my time step even further. So I used now 20 loops. So I put the previous time step by half. And what I see is nothing changes, right? So my value is still bounded. I still have a very good conservativity. The output here didn't change, at least not within the numerical accuracy. I mean, of course, if I compute several things more often, you learned about machine accuracy and so on, there are slight variations. That is to be expected, of course. But these changes we observe is within a range that we expect, that is acceptable. So this also strengthens our trust in the simulation because we have something of consistency, right? Remember all those kind of properties of numerical simulation. Consistency was one of that. If you reduce the time step, the results shouldn't change much. Of course, which is not if we go, of course, if we increase our time step, we become inaccurate and might see different, bad quality simulations. But if we reduce the time step further, we should, at some point do not get any different results. And this is the case here. Now I can also play around and increase, for example, the number of iterations by demanding smaller errors between iterations. All right, so I gave you here an excerpt from the command I was calling using Python. So you see again, I still use the 10 loops here, but now I'm giving a demand on the numbers of maximum iterations, which I allow. So I increase this number and I decrease the error value, which I expect the simulation to fulfill within the iterations so I can state that the iterative process converged. All right, so remember the lecture where I talk about iterative processes and that you always have at least 2 abort criteria. So what I do is, first of all, I increase my computational costs. All right, so the simulation takes more time to compute because now it's not done within one iteration, but it requires more iterations because I simply demand that this error value at the end has to be much, much smaller than based on the standard values. The result itself looks quite similar. If you compare maximum minimum values, you will notice, okay, the maximum volume has been decreased a bit. It's still conservative, it's still bounded. What could happen here is that because we're running now more iterations, we might have increased numerical diffusion because you will notice that the maximum volume here is lower than it has been in previous times. or in the previous simulations I showed you. But we will talk about numerical diffusion later on, which actually is a problem in the simulation. But that's just as a spoiler alert, right? But this is right, still nothing that would totally worry me here about it, because the change in tracer concentration is still on the, on the fourth digit of my calculation. So this is still something I would personally, depending on the situation, might consider acceptable. But of course, this always depends on the situation. So we have done that previous simulations, which you see down here, with a quite high spatial resolution. We can decrease that, right? What is the benefit of decreasing it? We gain speed, right? We reduce our computation costs. We have less demands on memory, or with less demands on computational costs. But of course, this influences our results, right? We have less dense spatial information, so we lose information. And what I also want you to keep in mind is we are generating a random fraction network. Well, not a random fraction network, but a random heterogeneity in hydraulic conductivity in the background. If we change our spatial resolution, of course, this also has influence on this artificial heterogeneity. So some of the changes we see here might simply be based on this different kind of artificial heterogeneity that we impose on the model. But this is the nice point, is you face similar problems if you're based on data sampling in the field. So even if you do kriging or some other things, this will always depend on your spatial resolution, right? But I will use this opportunity to introduce you to another analysis method. So these 2D visualizations are always great, but what I did here was I'm taking a profile cut through the raster map, and we can compare here and, for example, see that this spreading of the of the tracer concentration is much larger. Right, you have a way more distinct second peak here, which is only slightly indicated in the higher spatial resolution model. That again might be caused by the slightly different spatial heterogeneity here, but might also be due to an inaccuracy of the heterogeneity, because this kind of, once there is a gap, this tendency will be increased over time due to the coarser mesh. But again, the results are not completely different. The position of the tracer is still quite a comparable place. Again, you see the much wider spread here in the heterogeneous, in the coarser mesh. You might have also learned and remembered that for advection problems we have other criteria we can check besides the CFL criteria. For example, the Peclet number, I discussed that one in one of the other lectures, which is pretty much the spatial resolution multiplied by the velocity divided by the diffusivity. So it gives me a ratio of advective to diffusive problems, and it should be roundabout smaller than 2. So now I have a heterogeneous material, which means my velocity and my diffusivity are not equal across space. So for each cell I can calculate my Peclet number. Note that if you use some unstructured meshes like finite elements or so on, not with GraphGIS but with other software, also your dx will be different for each element. So that might also cause your different Peclet numbers even in a homogeneous aquiferic system. So to actually, in my simple example, to violate the Peclet number with obtaining Peclet numbers higher than 2, I had to switch to a very, very coarse mesh, right? So now I have a spatial resolution of only 10 meters. So of course, you know, with heterogeneity and so on, this is now barely comparable to the simulations I showed you before, but it's here just about the Peclet number. And to show you that you can do this, that you can analyze that kind of distribution. And well, we see, of course, this initial heterogeneity, which we had in the other simulations, is barely observable in this very, very coarse mesh. We see also that the tracer concentrations after 30 days have much higher values if you compare this with previous slides. We still see the problem is bounded. We have a remarkable loss in total mass. So here it seems that with a larger Peclet number, we lose our mass conservativity of the model, right? But again, this is an extremely coarse spatial resolution just to demonstrate this extreme effect. And we have seen that nicely before, that we can vary with our spatial resolution in quite a range to still be consistent and have similar results, which strengthens in total our trust in the simulation. So this here is just an extreme example to show the effect of the Peclet number, or violating the Peclet number with Peclet numbers larger than 2. I've talked or mentioned it before, numerical diffusion. I talked about the special issues of advective problems before. And this is something you can assess in any kind of numerical code, and I really recommend to do this also, especially if you're new to a software, you know, to get to know the strength and the benefits and the weak spots of a simulation. In GraphJS, in the solid transport model specifically, it is the case that you cannot put the diffusivity to 0, right? So that it might happen that the programs will just simply break because, for example, they're calculating something divided by this parameter here, diffusivity, and you can't divide by 0, so they are throwing you an error, or they just crash. So the bad ones just simply crash. But what we can do is we can put the diffusivity to a very, very small number, which is sufficiently small or close to 0. I did this in this example, and you can observe here the tracer concentration using this kind of small diffusivity, so mainly having pure advection. Remember that if we have pure advection, we would assume a shape conserving method. Means we're starting with a point source, we would expect to have this point source moving around with the flow velocity field. We do not see this here. So the this looks very diffusive also if we look at the maximum observable tracer concentration. We do not have any negative tracer concentration, so we are still bounded, but this looks like heavily diffusing. So you should remember we are operating on a heterogeneous background. So even if I have pure advection because I have a heterogeneous flow field, I have complex fluxes, what I see here might look diffusive, but could actually be simply based on advective processes, just to keep in mind. But, well, it still looks massive, so we want to dig a bit deeper into it. I therefore conducted a simulation with a homogeneous background. And, well, they're good and there's bad in this kind of simulation, because we see we're starting with this source here, and well, there is no numerical diffusion in y direction, which first of all is a good thing. So there are no fluxes coming in y direction. However, there is a diffusion in x direction, and that is kind of fundamental. I mean, remember that we're starting with the point source. We would expect having a point source moving along this line. Instead of that, if I do the profile again, I'm getting quite a bell-shaped distribution. To assess this, again, the statistics tool is quite interesting because, well, we see you have a minimum, we are still bounded, we have very good conservativity, right? So that's the best conservativity we had so far, no question. We have a homogeneous background that surely benefits numerical accuracy. But because we have a diffusive problem and we know that we can describe diffusive problems by these bell-shaped normal distributions, the mean value, but specifically the standard deviation, are interesting parts or interesting parameters to assess the amount of numerical diffusion we have, because this already is the standard deviation, so the height of this bell-shaped curve. And now you could look at this at different time steps, compare it with what you would expect for pure advective problems, right? But still want to point out that the maximum observed tracer concentration, also in the previous example, is much higher than what we would have in a if the diffusivity was ongoing, or if diffusion was considered as additional process, as physical process, not as just as a numerical process. So this is the question: what you might consider acceptable or not. I just also want to point out, and remember you at one of the very first lectures videos I was giving about groundwater simulation for exactly this sample, just looking at the flow, and I remind you that the groundwater flow module in CrossGIS had the trouble with precisely calculating the flow velocities in X direction. So it was giving us a slight, really just a slight, but it was giving us a slight gradient in flow velocity from left and right based on numerical accuracy, which we could not totally bring to vanish. And of course, this kind of gradient would cause a similar phenomenon here. So this is numerical diffusion, but this numerical diffusion might have different sources. You know, it might be just simply a problem of the transport part, so of the advection, but it might also be routing back to the inaccuracy in the groundwater flow module, which provides us with the velocity field that might cause such kind of spread. So there are multiple causes now which we could start to work on and to improve. So we could now, for example, go back, conduct the groundwater simulation, demanding even higher accuracy in terms of number of iterations and the board criteria for the iteration in terms of accuracy. But we could also, you know, if we would be developers, digging into the code here and try to reduce or improve the implementation of the advective transport module. Right, so they're different now. Like if there would be your simulation, there would be now different points of access to improve the quality of your work. But you say that how simple it is actually to assess and to check for the effect of numerical diffusion on your problem. Coming to an end, I want you to take home a couple of key messages. What do you understand as the quality of the simulation? So it'd be something being a good or bad model. There are very different approaches to this, and they depend on your perspective and your demands on the simulation. Especially conceptual decisions are difficult for you to check, really rely on the documentation of the model. This is things where you know, when you get a simulation and you rely on the simulation, or you're tasked to check it because you're working on public service or something like this, and the documentation is bad, this is something where you know have to ask questions to the person who conducted the simulation, and so on. You saw some very simple things that can be checked. For example, boundedness. Most programs will allow you to check for mass conservativity, so giving you some kind of mass balance, or so on. This is something you can check very easily for your own simulations as well as for others. Know and check your stability criteria. They're independent if you're conducting the simulation or if you're checking the simulation or something else. Know your stability criteria. Look for possible hints in the simulation that show you that the simulation has not been conducted appropriately, like violation of boundedness, violation of conservativity, unexpected regular patterns that shouldn't be there, right? Things like this, as I have highlighted in this short talk, things for you to check and give you an idea about the quality of simulation, right? Especially in the corners or so on boundary situations, because many of those structures would arise close to the boundaries, as it has been in the example I just showed you. To really quantitatively assess the accuracy of a model is difficult if you have no data for validation, or if you dig really deeply into the code and assess the different error levels throughout the code. But again, you saw, for example, in this lecture here, how you can have variations and check for accuracy and sensitivity, for example, to timestep, to parameterization, to spatial resolution, all those kind of things, and see how what the range is there in the accuracy, or how much those basic things affect the outcome of your simulation. Also, a simple check, which is always recommended, to check for convergence in spatial and temporal resolution, right? Just simply vary the spatial resolution, reduce or increase it. Same for the temporal resolution. And of course, as coarser you get, as more inaccurate your simulation will be. But the important thing is, as finer you go, you should come up into a state where your simulation results do not change outside of the numerical accuracy or the machine accuracy anymore. So this is also something where you can have a lot of trust in if your simulation is consistent in space and time. Thank you very much for your attention, and have a nice day.